Yeah, in the last class, we have studied about the lasers. In that, I have explained the basic principles of the laser, that is your spontaneous emission, then the absorption and stimulated emission. And then we have discussed about the laser configuration. In that, I have described about the Fabry period resonator. So I'll just brief out this thing. Yeah. So in the last class, I have explained about the laser, and I've explained about absorption, spontaneous emission, and stimulated emission. So with respect to the diagram, and then I discussed about the modes. So we have the three types of modes in which within a light you have electric field as well as magnetic field. So the light consists of transverse electric mode as well as transverse magnetic modes. So within that, how it actually comes out of the laser is dependent on whether it is a longitudinal mode or a transverse mode or a lateral mode. And then I've explained a Fabry period resonator, so how it emits the light. So the next one, so if they ask if they may ask a Fabry period resonator, or they may ask a DFB laser, so which we will be discussing this time. This I've explained. So this is the resonant frequency where the amplification of the light will be maximum in Fabry period resonator. Okay, so if they don't ask Fabry period resonator, they'll ask DFB laser. Okay, so this is second configuration of the laser. Same principle, the principles of absorption, the principle of spontaneous emission, the principle of stimulated emission will come into picture in the DFB laser also. Okay, so you have a confinement layers. So this is the confinement layer. Okay, so here you see I have written this is a confinement layer, and this is also the another confinement layer, one confinement layer, another confinement layer, and yeah, this is another layer. These are connected to the positive terminals and negative terminals. So if it is a P type material, it is connected to the positive terminal. So the input for any laser is the current pulse. So the electrical current pulse, it's the input, it converts it to light. So that is your laser. So whenever the positive terminal is connected to P type material, all the holes are pushed into the active layer. Okay, so similarly from this side, it is an N type material, N type gallium aluminum arsenide or N type gallium arsenide. Okay, here it is a P type gallium arsenide or a P type gallium aluminum arsenide. So from this side it is a P type, from this side it may be N type, or this side can be N type, or side can be P type. Then you have to connect positive terminal here. So whenever you connect these similar terminals to the P type and N type material, so here if it is a P type material, the holes are injected into the active layer. If it is a N type material, the electrons are injected, negative plus electrons are pushed into the active layer. So in this active layer, you have electrons and holes. So it is a double heterogeneous structure itself, same whatever we discussed in LED. And the recombination of electrons and holes will happen in the confinement, in the active layer. Okay, so that recombination will leads to the light. Okay, and generates an energy that is from your two things. Initially, the electrons and holes will recombine. Okay, so absorption may take place, or once they recombine, they generate a energy, they generate a light. So that is spontaneous emission. One, the spontaneous emitted photon will again hit the electrons and holes which are present in this particular layer. Again, there will be a release of energy once the photon hits it. So that is spontaneous emission. Okay, so all the three things, absorption will be there, spontaneous emission will be there, and stimulated emission. All the three things will take place in the active layer. Okay, and generates a light. And the only difference between LED and laser is the laser generates a very directional beam. Okay, so this is your substrate. This is also is a substrate. So another, the one difference between DFB laser and your Fabry period laser is there we have a reflector. Here you have a grating. So this is a grating kind of structure which is over your structure of your LED. So this grating kind of structure will have a, this is called as Bragg's grating. Okay, this Bragg's grating will have a different refractive indices. So this will contain a different refractive indices compared to this. This will have a different refractive indices compared to this. So what this actually will do, will get a different energy bands and will push the electrons or will push the photons to one side. Okay, and on this side you have a reflectors. So whatever the electrons and holes which go to this side, they will push that. There will be a reflectors which will be present. They will push that electrons and holes into this particular region. This will also do the same thing. This will reflect the light and send that light photon back to this for this particular area, so that the light generated will be very directional. Okay, there in case of Fabry period resonator, you have a mirrors which are also the reflectors. Here one side there is a reflector, another side there will be a feedback grating which sends the light again back. Procedure is same, but this uses a corrugated feedback DFB laser or DFB feedback grating. Okay, instead of your mirrors in case of Fabry period resonator. Explanation you can write it same, and you can in the exam you can write it about stimulated emission, spontaneous emission, as well as absorption. So normally it will be asked for 8 marks. Sometimes it may be asked for 10 marks also. So a detailed explanation is needed. Okay, so it generates the light and the light will come on. As shown in the figure, the cleaved facets are not required for the feed. The cleaved facets are present in Fabry period resonator. Here we have not used. Instead of that, we have used a Bragg's reflectors, that is called as grating. Fabrication is similar to Fabry period type, except lasing action is obtained from Bragg's grating or periodic variations of refractive indices which are incorporated. Because due to Bragg's grating, you have a different refractive indices. Okay, the general output is needed only from the front facet, so the light will come out from the front facet. Okay, so reflectors also reduces the optical losses. You can explain in detail, okay, with respect to this. Okay, you have to see based on the marks which is allotted to it and explain. So you can include stimulated emission, spontaneous emission, absorption. You can include your own explanation. Then you can include about the layers which are present in there. You can include about the how the light will come out from this. Many things you can include based on the marks allotted to it. Okay, so the glazing conditions, so you can include this also in your DFB laser. Glazing conditions and resonant frequency, it is a frequency at which your amplification take place, that is spontaneous emission should happen. All the photon should hit the electrons and again generate a photon. So that is the at which frequency it happens, that is your resonant frequency. The glazing conditions, and we'll see that. So the electromagnetic wave which is coming out in the longitudinal direction, whatever we have shown, that is given by the electromagnetic wave with respect to time and the direction at which it is coming is given the current which is generated and the exponential increase. Okay, initially why it is an exponential increase? Because spontaneous emission, the photons emitted will hit the electrons and holes, again generate another photons. Those photons again hit the electrons and holes, again generate photons. So it's an exponential. Once that lasing condition, initial condition is reached, then amplification will happen exponentially. So that is the meaning of that equation. So it depends on the electromagnetic wave, depends on the current which is generated in that direction, as well as the omega, which is the frequency, that is your frequency in terms of radians, and omega or W you can write. So beta is the propagation constant, Z is the direction. So that is the equation for the electromagnetic wave. What is the electromagnetic wave? The light itself is your electromagnetic wave. So then what is Ez? Then what is IZ? IZ, what is the current? The current expression can be written with this particular expression. IZ is equal to I naught e raised to this particular value, where h nu is the energy. E is equal to h nu is the energy which is generated from that light. Okay, Z is the direction from which. In that, alpha is effective absorption. This is absorption. Some of the photons will be absorbed to jump. Okay, it will not generate the light. So that is the initial phase, that is absorption. So absorption will consume the energy, will not generate the light. The next steps are, once absorption is done, next steps are emissions. Okay, so absorption you have to minus with respect to this particular. So this is your current in that particular direction is equal to the current in the first point. So initially that active layer, at the active layer point. Okay, exponential increase with respect to this tau, fraction of optical power in the active layer. So how much optical power is present? Fraction of that. Okay, and G is the gain, which is the gain. How you get the gain? once spontaneous emission happens, there is a gain. Okay, photons are generated frequently. That is the gain. Gain, which is the function of energy, because once the more photons are generated, more energy is generated. What is energy? H nu. So that much will be the gain. Gain, which is a function of energy, multiplied by the fractional power which is generated. So which is the things to be minused in that? Minus is absorption. So which is not generating the energy. This is an absorption coefficient. Absorption of what? Absorption of energy. Energy is H nu. So in which direction? Z direction. Okay, so that's how the IZ is noted. Okay, same whatever gain coefficient, photon energy, distance traverses along the lasing cavity. So those two expressions you can write. You can remember it and you can write. And if you understand, very easy to remember. Okay, so the lasing condition happens when the light gets reflected back. If you observe this, so the light, whatever the photons which are generated will go in all the directions. I explained about that. So that has to come in this direction only, because due to that gratings and reflectors present, they send the light in this direction itself. They reflects the light and sends the light. They reflects the light and sends the light. So when that happens, it is maximum when Z is equal to 2L. That is what the meaning. Okay, so here it is. Lasing, that is light application, occurs when the gain of the modes is equal to the optical cavity, where L is the distance of the optical cavity. So you have a reflector, you have a fabric grating here, the distance between them is L. If it is 2L, then they have found out that maximum amplification takes place. Okay, so this condition you should remember. That is, after research they got that Z is equal to 2L gives you the maximum lasing condition. That is, amplification will happen. Okay, R1 and R2 are the reflectivities of the material. So you have a reflectors at the edges, no, at the end. So what is the reflectivity of that? Again, it depends on the material. So those reflectivities are R1 and R2. One is from a grating, another one is from a reflector. So in that case, the current is generated after it comes out from that particular lasing area, right? So when it comes out, when Z is equal to 2L, then just replace Z is equal to 2L wherever you have. So Z you are having earlier here. So 2L and 2L is replaced. So this, once you remember one equation, you can write down the other equations also. Okay. So for maximum lasing condition, so that is after some distance, right? So maximum lasing will happen at the active layer itself. Okay. That is at this point. I'll just show the diagram. At this point, okay, maybe after this area you can take it as 2L. Okay, so light will reflect and then it will come here, but at I0 you will be generating the light. Maximum recombination will happen here. Okay, once the light comes here, so that is I2L should be equal to I0, where maximum this one will happen. So that is the meaning of that. And phase should be same. Phase should be same. So there should not be any phase difference between the photons. If the phase difference is different, then what happens? Then they will not add up constructively. They will add up destructively, because one is a sine wave, another one is a cos wave, means they will not add up correctly. So that's why perfect lasing condition should have I2L is equal to I0. That is at the active layer. The recombination should happen at that point itself. And phase, the photon generated phase, there should not be any phase difference. That is theoretical concept. Practically it is difficult, but most of the cases it generates. Okay, that is the lasing condition. It is designed for that. So in other words, you just replace whatever the conditions I have put here. Optical gain at the threshold is equal to total loss of the capability. There is another thing. So the gain, so minimum, the gain should be at least equal to the loss. If the losses are more in the cavity compared to that of gain, then there will be no lasing action. There is no amplification. So at least it should be equal to this. So if you put all these equations in here, that is I2L is equal to I0 you put, and e raised to z, this one you make it as 1. Then if you solve that, you will end up with an equation called as this. Okay, where tau GTH, tau, where is tau GTH? This is tau GTH. GTH in the means G energy, that is gain. Okay, so for that you get this particular expression, where alpha we will take it as where alpha is the alpha GT. Okay, this will take it as alpha T. Okay, which is the loss on the cavity. At least alpha T will take it, and just replace it. We'll find out this particular expression. Okay, where R1, R2 are the reflectivities, 2L is the reflectivities, distances, and all these things. So these equations you can remember if they ask. So if the DFB laser is asked for 10 marks, then you can write these equations also. If it is for 6 or 8, 6 marks, then expressions are not necessary, but you can use all the definitions, okay, whatever I explained. So once you know the lasing conditions, if any problem is asked, directly you put that alpha is given, the L is given, R1 and R2 is given, then you can solve that. What is the gain at the laser? So it is just for your reference. Normally they'll not ask, they are not asked that. Okay. Next is power current characteristics, where power and current characteristics is how the power of your laser will increase. So with respect to the current is in X direction, optical power is in Y direction. So initially the electrons and holes will come to the active layer, they will recombine, they start generating the power as well as the light. From that light there will be some power, and this will be slowly increasing. Okay, up to this condition there will be spontaneous emission. What is spontaneous emission? No photon is used for generation of light. The just the electrons and holes will jump from valence band to conduction band by taking by releasing the energy. Okay, that is spontaneous emission. So once after spontaneous emission, the generated photons will again hit the electrons and holes and generate another photons, which leads to amplification. That will happen in this case, and there will be a drastic increase in current and power. Okay, so that is your power characteristics. So laser will absorb the light, then spontaneous emission will take place up to some time. After that there will be a stimulated emission, which leads to amplification and generation of the light. Okay, that is this power characteristic. Whatever I explained, it is here. Okay, so yeah, with respect to expression, it is given like this: GTH is equal to beta JTH, where JTH is the current density, and this is the optical gain. Optical gain will be B times of the current density, where beta is the constant, which is dependent on device characteristics, that is depends on reflectivity, that is dependent on drag ratings and all these things. Okay, so next is external quantum efficiency. For external quantum efficiency, we have derived for LED. For a laser, there is no derivation, just an equation is been given in your textbook. So that is this equation. So quantum efficiency, how much light is coming out with respect to how much electrons and holes pair are present in the active layer. So that is your external is how much light is coming out from that. So that is this one. So n next is equal to neta next is equal to neta high. This is the internal quantum efficiency. So which is around about 60 to 70%. Of 60 to 70% of electrons and holes will recombine, and out of that how much will come out is your external efficiency, which is zeta th is some threshold, and alpha is the absorption coefficient. You have to minus that because some photons will be absorbed and then generated light, so that is minus absorption. Okay, that is your external quantum efficiency. Okay, resonant frequency, at what frequency the light is generated is given by some lasing conditions. So threshold lasing is given by this equation. This you have to remember, 2 beta L, where beta is the propagation constant, which is given by 2 pi m by lambda, which is very basic, which I explained in the first chapter. And m is an integer. Okay, whether it is 1, 3, 5, we'll see that. Okay, how that m is dependent, m is dependent on this one, m of that particular lasing material depends on 2L, where 2L is the distance between your Bragg's grating and the reflector. So this is the distance, and it is n is the refractive index at that point, and the lambda is the wavelength. So this can be replaced with c. Okay, or lambda can be replaced with c by v, or the frequency. Okay, c by f. Okay, so in some cases they will write it f, or in some cases they will write it. Yeah, so now we know that lambda is equal to c by f. You replace it c by f, then c by f or v, then it comes to this. So m, the integer m is dependent on the frequency, then you can replace in this point. So this is the main lasing condition. To this you replace m and get the frequency f. So how to get f? M is linked to lambda. From lambda you can link it to f, then you can replace here to get your lasing condition. So from that you get, yeah, same thing. So this is for a gain. How you calculate the gain? Gain is also again dependent on a certain equation which is called as G lambda. So G lambda is equal to G naught, where G naught is that the active layer, at 0 position, which is the maximum gain. And after certain wavelength, after certain, this is the center wavelength, after different wavelength, if the light is generated at different wavelengths, there will be a reduction which is given by this. It almost resembles your Gaussian distribution. Okay, so see, for a Gaussian output, this is the one. Not so important, but resonant frequency is important. Okay, so resonant frequency, you write this, and then we have stopped at this point, right? Now you replace M, you get an equation called as delta F or delta V, or frequency. This frequency is dependent on the velocity of light in the vacuum and the distance between the Bragg's grating and the reflector and the refractive index. So this you can remember. And then what is the lambda? So how much lambda is generated? So some of the light is generated 0.6 micrometer, some of the light is generated 0.61. So there will be a slight change in LED wavelength. That wavelength is given by this expression. So not so important, but just remember the equations. Okay, next is spectral and spatial distributions. Important things are Fabry period resonator, then DFB laser. Okay, so spectral and spatial distributions of LED. How the LED output and laser output will look like. See, so a laser output is very directional and it is narrow. This is laser. LED, this is with respect to wavelengths within wide band. So it's a narrow band. LED is of wide band, and power generated will be same. So this will go in different directions. So people sitting at this point can see with respect to LED, but laser is very directional. Okay, so how with respect to spatial distribution, so this is your laser. So output power will be maximum at this direction in case of laser. At other sides it is less, but LED it's different. Even though it is very maximum at the center, it also distributes on the surroundings. That is your LED. For short distance application, for display purposes, use LED. For directional purposes, in case of OFC, where you have to send the light, then you can go for laser. That is the meaning. So advantages of laser: simple, economic design, high optical power, and also it can work at high temperature. Coupling efficiency, because as it is directional, you can couple it from one cable to another cable very easily. Low spectral width, very directional, and maintenance is easy, and transmit power will be high. So those are the advantages. Disadvantages are there will be a speckle patterns. What is the speckle pattern? You see, observe here. So this is the speckle pattern. Okay, there are chances of speckle patterns also which will come out from the laser. So that is one thing, and it is extremely sensitive for loads. So that is another disadvantages. Okay, so in this particular module, LED and lasers are important. So with respect to the optical emitter, characteristics of optical emitter are the requirements of optical emitter. First one, which is important, and then double heterogeneous structure of the LED, which is important, very important. Then I've discussed about surface emitting LED and edge emitting LED. Those are also important. And apart from that, next we have discussed about the quantum efficiency and LED power, which is also important. Quantum efficiency and LED power. Then in laser, DFB laser and Fabry period lasers are important. So normally they'll ask in the last paper, 1.5 questions was asked in these whatever I explained in these concepts itself. Okay, this completes almost the 2.5 modules which are allotted to me, and I stop my share.